Okay, so where are we? We were at how many grams of sulfuric acid are needed to react with 1.5? No, we did that one, so 22. A burning candle is placed into a glass jar. The jar is then closed. The candle burns for a few seconds before going out. At the end of the reaction, the candle is still present. Identify the limiting reagent. Well, the candle is still present. The fire was never really part of the reaction, so there's only one thing here that could actually run out, and that's what you will run out of if you were inside of a closet that's on fire: oxygen. In lab, you decided to mix solid zinc with a clear solution of hydrochloric acid. During the reaction, you see hydrogen bubbles, H2, and also determine that a solution of zinc chloride forms, ZnCl2. You also notice that all the zinc solid is now gone, but 5 moles of HCl remains. Okay, not a problem. Zinc is my limiting reactant because it's all gone, it's disappeared, and there's plenty of HCl, and HCl is in excess. Okay, 3 factors that affect the rate of solvation. I hope you remember this. It's shake, bake, and break. And breaking increases surface area. I want you to remember that. And baking is just adding heat. And shaking is stirring or agitating. I'm just going to put stirring here. Stirring, RR, whatever. Okay, as temperature increases, what happens to the solubility of? Well, let's get a solubility chart and let's look. Okay, so these are all my solids, and as temperature goes up, the solubility on all my solids goes up, 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 up. But the solubility on my gas goes down as temperature goes up. This is my gas. So solubility, as temperature increases, the solubility of a gas goes down. Solubility of a solid, especially ionic solids, goes up. That's pretty easy. Okay, where are we at now? We are on to the last page. All right. So pressure increases, decreases, or has no effect on the solvation of a solid. Pressure has no effect on the solvation of a solid. Pressure increases solvation of a gas. That was where that 10 degrees, 2 atms, atmospheres is a measure of pressure. That's why 10 degrees, 2 atms was the answer on your test, because this is a larger pressure and this is a lower temperature. But it has nothing to do with solvation of a solid. We know what has to do with the solvation of a solid. Shake, bake, or break. All right, process of solvation. Well, okay. Let's see. I don't want to write it all, so I'm just going to explain it all. So, solvation. Let's say we have C6H12O6 here, and we have one mole of this, and it's just various molecules of this, and they're in this nice structure like this. C6. Each one of these is one molecule of this, and they're in a nice lattice structure, also known as a crystal. Well, what happens in solvation? All these separate. All these particles separate from each other, and they are surrounded by water, right? Depending on how they're charged, and it could just be randomly surrounded by water in the case of this. So this is C6H12O6. So all the molecules separate, and they are surrounded by the solvent system. This is the solvent system. It's surrounding these molecules, and it keeps them separate from each other. So all the other molecules are separate from this one because there's water in between. And we know what happens in solvation of an ionic compound because we've shown that before. NaCl. Hopefully I've drawn that picture enough. When it goes into water, it goes into water as NaCl, and then it dissociates, and after it dissociates, then it gets surrounded by the solvent system, right? And hopefully I've drawn this picture enough to where everybody knows that it's surrounded by the solvent system. Okay, Batman must drink a cup of coffee each morning or else he is very cranky. Chaos is about to start in Gotham. Okay. So you need to help him dissolve the sugar in his coffee quickly. What would you politely suggest Batman to do to get his sugar to dissolve? Let's see. Keep the coffee hotter. Hotter, hot. Let's see. What do we want to say here? What do we want to say here? Brew the coffee at a higher temp. We can use powdered sugar. Part of that break. Powdered sugar has the highest surface area. You can't bust it down any smaller than that. Okay, Batman's sidekick Robin only drinks Sprite in the morning. He woke up late in the Batcave, so he was not able to finish his delicious drink. He knows if he leaves the Sprite on the counter, it will taste flat. What can he do to keep his frosty beverage from becoming flat? Put it in the fridge. Because we know at lower temperatures we can keep more gas dissolved. So put it in the fridge. You can also cap the can. They make those little lid things that you can put on top of the can. It basically prevents the gas from just flowing out. You're keeping it under a higher pressure because as the gas comes out, it becomes higher than atmospheric. If you keep it under that cap, then it keeps the rest of the gas. So let's say we have a can of Coke and it's half full. Well, you have 1 atmosphere of pressure pushing down. And so that's not necessarily going to keep everything dissolved, even when it's cold. All the gases will come out, right? But if I put a cap on that, after some of the gas comes out of solution, it will make this pressure be higher than 1 atmosphere. And it basically will prevent any more from coming out of solution. So capping the can and putting it in the fridge, about 2 best things you can do. What is the molarity of an aqueous solution containing 90 grams of C6H12O6 and 2.5 liters? Well, we can't do anything with grams, can we? So let's shift this up here so that I can show you what we're doing. Okay, so the formula for molarity is big M equals moles over liters, right? But we don't have moles. We have grams. So we have to go from grams to moles. So we have 90 grams C6H12O6. And this is going to be 1 mole, and this is going to be grams C6H12O6. And so I need to do a little bit of calculating, figure out what my molar mass is that's going in right here. So on 12 times 6 equals plus 12 equals plus 6 times 16, which is the oxygens, equals 180. 180, 90 divided by 180 is 0.5. So we have 0.5 moles. Maybe I should put it out here. 0.5 moles. Nah, that's not going to fit. C6H12O6. Now we have moles. We have 0.5 moles. What else do we have? We have 2.5 liters. 0.5 divided by 2.5 equals 0.2. So equals 0.2. That is our molarity. 0.2 molar. I told you were going to get tired of that word. Molar, molarity, molality, moles. Okay, what is the volume of 2.4 molar LiCl solution that contains 176 grams of LiCl? Okay, so this is the same molar problem. Let's just turn this over so I can get a clean piece of paper to work on here. There we go. Now we're cooking. Okay. So how many grams? Okay, so we have 2.4 molar equals 176 grams over X liters. So we have to figure out how many moles are in 176 grams of LiCl. Same thing over and over again, moles to grams, grams to moles. You're going to do it forever and ever and ever. Grams LiCl. So we have an Li that is 7 plus a Cl that is 35.5, 42.5. 176 divided by 42.5 equals 4.14. 4.14 moles. 4.14 moles. And remember what I said, these two can just switch places. So 4.14 divided by 2.4 equals 1.7x equals 1.725 liters. 1.725 liters. Okay, how many grams of CCl4 should be added to a solution to make 2 liters of a 6 molar solution? So now they're just looking for this. We have to figure out moles. X moles equals 0.6 molar over 2 liters. So we have 2 times 0.6 equals 1.2. 1.2 moles. Oh man, I'm wandering off here. Let's set that there. And then we have to convert moles to grams. 1.2 moles of what are we converting? CCl4. CCl4 over 1 mole CCl4 is how many grams of CCl4 equals. Okay, so CCl4. So Cl is 35.5 times 4 plus 12, which is my 1 carbon. 154 grams times 1.2. That equals 184.8 grams of CCl4. So that is my answer. 184.8 grams CCl4. Oh, okay. So let's get rid of my scratch sheets. Let's see if we need any of this anymore. I think we might be in the home stretch. Okay, colligative properties depend on the identity but not the number. Nope, the number but not the identity. Yep, that's it. B. It's the number, not the identity. What happens to each of these colligative properties? This was so disappointing on that test that people just spaced out and didn't think about what colligative properties. So vapor pressure, depression. That means it goes down. Boiling point, elevation. That means it goes up. And freezing point, depression. That means it goes down. Which compound will lower vapor pressure more in a liquid? Well, here you go. This is 0.1 molar, and molar, I want you to think about this. Molarity equals moles over liters of solvent. So it's basically concentration of this solute, right? The one with the higher molarity is always going to win in colligative properties. Okay, how would you prepare 1 liter of a 4 molar MgO solution? Well, so if it's 4 molar and it's over 1 liter, that must mean that it's 4 moles. That's the only way you're going to get that. So I need 4 moles. So I have 2 where I dissolve 4 moles. This one dissolve 4 moles in 2 liters of water. But that would mean that once I dissolve my stuff in 2 liters of water, it would be higher than 2 liters. It would be 2.1 liters. So that's definitely not the answer. Dissolve 4 moles of MgO and add enough water to reach the 1. Ooh, that should be the 2 liter mark. There's no right answer here. How about that? The 2 liter mark. So I'm going to go with C with the correction that I made. I hope that helps you guys out. I hope a bunch of you watch it. Have a good night. Don't study too late.